Testing. Is Zhao Xilei here yet? Zhao Xilei. Oh, you're Zhao Xilei. Okay. Are you happy with my answer or no? I edit my answer. You haven't seen it? Okay. But the previous answer, you already see it or not? Not yet. Okay. Do you want me to discuss here or what? No need? You sure? Okay, let me know again if you want me to discuss it. I already reply you in the Moodle. Okay, you let me know again. See you. You let me know again. Okay. All right. Good afternoon to everyone. Welcome back on a fresh weekend. Since we passed by the Q&A question, since we have a test on determinant and vector space, let's do some revision or some thinking. If I ask you, what's the determinant of the following matrix? What do you think? What's the determinant of this matrix? 0. Why? Okay, it's a triangular matrix. Okay, so say it is triangular. So determinant, it is the product of the diagonal. Okay. Another way to see it is determinant can be calculated using cofactor expansion along any row or columns, right? So if you row cofactor expansion along the 0 row or 0 column, you also get 0. Okay. Okay. A few more about vector space. Okay, let's talk about one of them. So thinking deeper section. Okay, let's think a little bit deeper. Okay, every time you hear me talking about 0 vector, 0 vector, 0 vector, right? Okay. But really, 0 vector is the thing that when you add to it, you get back yourself. So it is a different form in different vector space. Okay. So when I say vector 0 vector in Rn, 0 vector in Pn set of polynomial, they really mean different things. But they have a property that like a number 0. Okay. When you add any number to 0, you get the number back itself. Right? Because 2 plus 0 is 2, minus 1 plus 0 is minus 1. Okay. So 0 vector is doing the same thing in different vector space. So let me give you some vector space and then you tell me what are the 0 vector here. The vector space I list out here are those that we learn in class. These are all example of vector spaces. Okay, first tell me what's the 0 vector in R2? 0, 0. Okay. So 0 vector in R2 is 0, 0. because anything in R2 will looks like x1. Okay, tuple number. How about in R3? Huh? What's the zero vector? 3, 0. Okay, 1, 2, 3. Because anything in R3 looks like what? What's the general form of R3? X, Y, and Z. Okay, 3 tuple. Tuple of 3. Rn, n0. Okay, so you got n0. N0. So in Rn, in general, you will write as x1, x2, up to xn. How about Pn? Huh? So it's 0. So in Pn, so what's Pn? So Pn are the polynomials that have degree at most n. Okay, so it's like x a0. Okay, I use t in this case. So a0 plus a1 t plus a2 t squared plus dot 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 up to a3 t n. Okay, so what's the 0 here? So it is 0. Okay, we put 0 here. This 0 means 0 polynomial. Okay. So what does 0 polynomial means? So 0 evaluate to any number, you get 0. Okay. This is the. Okay. Can I see how many of you is taking advanced mathematics now, together with linear algebra? Can you leave up high? I want to see how many of you. Higher. Advanced math. Only here? Oh, okay. Anyone took it before? Before? Oh, took it before. Okay. 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 So Pn is the 0 polynomial. How about set of infinite sequence? What's the 0 in set of infinite sequence? What's the 0 here? What's the 0 vector in here? What's the sequence that when you add to it, you get back yourself? How do you add two infinite sequence? Huh? Say again. Negative? What do you mean? Okay, so what's the 0 vector? No. The 0 vector is unique. Doesn't depend on vector. What's the sequence that you add? So what's the general elements look like here? It's an infinite tuple of real number. Okay. What's the sequence that when you add to the infinite sequence, you get back the original infinite sequence? Idea? How do you add two infinite sequence? Yeah, just add one by one. So you need to make sure that every part has a one. So for 0 vector, you need to make sure every part has a 0. Okay. So you have an infinite 0. Right? Because a0, a1, a2, dot, 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 plus 0, 0, 0 is equal to a0 plus 0, a1 plus 0, a2 plus 0, and then dot, dot, dot. Okay, so you get back the original sequence that you add to 0 vector. Make sense? Does it make sense? Make sense? Okay. So this means that when you want to figure out what is zero vector, actually you need to figure out how to add inside a vector space first. So this addition will very much affect what is zero vector in the space. Okay. Okay. So what's the zero vector in set of real values function? Zero vector times x. I mean, it's just zero, right? Okay, so it's the zero. In this case, we still put zero here, and this is called the zero function. Okay, so zero function means if you evaluate at any point, you get zero. Okay, so these two space are quite similar, right? If you have done the tutorial question, I think I wrote that Pn is a subset of continuous real value function. Subspace of. Okay. And why is it infinite? If you learn calculus before, you should learn Taylor series, as mentioned, Taylor series. Okay. If every function can return, every continuous function can be approximate using Taylor series, but Taylor series is infinite. So when you approximate a function using polynomial, you need to use infinitely many terms to approximate it. Okay. So what is calculus? Calculus is actually doing on vector spaces. Okay. So doing infinitesimal calculation on vector space. Okay. Some more, a few more before we start. Two more. Okay. This is also another one coming up from a discussion with one of you. So in the linear transformation, we require that TCX is equal to CTX. Okay. Anyone think about what's the geometric meaning here? Okay. So let me guide you a bit. So what's CTX here? Okay. TX, this one is for all C. Okay. So TX here is a vector. So TX here is a vector. How about CTX? Scale of this vector. Okay. So everything along this line is CTX. Okay. How about CX? It's an X. And then everything along the C. Okay. This means what? The line in the codomain is coming from a line in a domain. Okay. A line in the codomain is coming from a line in a domain. Okay. Similarly for the other one. So two property, right? Preserve vector addition and scalar multiplication. Similar for this one. Tx plus y is equal to tx plus ty. Okay. So tx and ty span a plane, right? If you remember, when we add two together, there's form a plane. Okay. And then this plane is coming from x plus 4. Okay. So the plane in the codomain is coming from the plane in the domain. Okay. This is what this two property of linear transformation doing. Okay. So when T is a linear transformation, this means you send line to line, send plane to plane. Okay, make sense? Okay. So that's why you learn determinant. So determinant will see how the plane change, the area of the plane change. If the determinant is greater than 1, then the area become larger or something like that. Okay. And there's another branch of mathematics that study the area which doesn't change, and we call it a symplectic geometry. So symplectic geometry study those things that doesn't change the area, where the difference of the area is 0. Okay, so linear transformation just study how you send line to line, send plane to plane. Okay. Yeah. And one last thing before we jump into today's story. So this one is I want to wrap up this story here and then clear some confusion. So the vector space isomorphism. Vector space isomorphism. Let me tell you the whole story and then we clean out this part. Okay, so let's just take P2, okay? P2 and R3, okay? So when I talk about these, right, these spaces, right, immediately you should think about some space, okay? Because they are originally a space. It's not just a simple P or just a simple R, right? It's a space. So what is the thing leaving the space, okay? So you need to immediately know what's the general thing living inside here, okay? So meaning the set contain what? So P2 contain what? Degree set of polynomial of degree less at most 2. Okay. Maybe use T again. 8. Okay. And R3. Okay. R3 is what? 3 tuple of numbers. A0. Okay. So last week we see that these space are isomorphic. Okay. They are isomorphic by the coordinate vector. When you take the coordinate vector with respect to the basis. So this means I need to tell you what's the basis now. Okay. So basis in this space, I will take 1 t and t squared. Okay. You can see that why I want to pick this, because you can see that all the elements here are linear combination of these three. Okay. How about basis on the other side? So let me call this C then. This side is I pick 0 and 1 0 0 0 1 0 0 0 1. Okay. Similarly, you can see that all the vector here is expressed as a linear combination of these three guys. Okay, makes sense? Okay, cool. So they are related by this map here. It's an isomorphism because I proved that this is 1-to-1 and onto. So in general, if you know that it is a map is 1-to-1 and onto, then you can produce an inverse. So this map is invertible. I didn't tell you this, but I tell you now. So if it is 1-to-1 and onto, then you can go back and forward because you will have an inverse map. So the question is, if they are isomorphic, does it mean that P2 equals to R3? Are they equal? Are they equal? Is P2 equal to R3? Why not? What? Yeah, is P2 equal to R3? Yeah. Equal some guy. 子堂 is 三子堂 here. Okay. So is P2 equals to R3? Why? Say again. Say again. But polynomial is a vector space. Set of polynomial is a vector space. Okay, the key here is they express differently. Okay, so their elements look different. Okay, one looks like this, the other looks like this. Okay, they are different on the nodes, but as a vector space, they are the same because they have the same structure. Okay, if you extract out these coefficients, they just operate the same. This is called vector space isomorphism. Okay, and last time we say that there's an invariant of this vector space. Okay, since they are the same, so this similarity should be demonstrated by some object. Okay, and then this object is what we call the dimension. Okay, so after we take dimension, what do we get? What's the dimension of the two space? Huh? What's the dimension of this two space? 3. Okay, because the dimension is the number of basis element. Basis element have how many? 1, 2, 3. 1, 2, 3. Okay, so they both represent 3, but they are different. Okay, so this corresponds to the slide I put on Moodle here. Okay, what did I put on Moodle? I'm not sure how many of you read the slide. Let's see, where is it? Have you seen the slide that I draw a few ships? This one. Okay. So one might be the same, but every ship is different. Yeah. So above 3, we can put 2 different vector space. Yes. Okay. Okay. I know some of you complain, right? Maybe I'm not sure complain or what, or comment, complain or comment. Maybe you think the way I'm teaching a bit abstract. Okay, I actually I am abstract because I'm from pure maths. So also there's a good thing, there's a bad thing about abstract, but I want to advocate abstract. Okay, so what's good about abstract? When we talk about abstract, right, we can what in one time deal with different objects together. Okay, for example, I don't need to tell you how to do P2 calculation or Rn calculation. I can straight away tell you one calculation that you can do on both steps. Okay, so this is the thing being abstract. So for example, in your how you apply in your work. So when maybe you come up with a project, okay, you tell your boss, this project can work for this situation. But if the boss asks you, how about the other situation, work or not? So you need to go through again, right? So instead of doing that, you just say, if all the situation satisfy this condition, then they all work. So you prove to your boss, right? Yeah. So this is how abstract work in the life. Okay. So one more thing is abstract is not as what you thought. Okay. Abstract should come from concrete examples. Okay. So first they do calculation on P2, then they do calculation of vector space, and they realize that these two has some similarity. So we abstract out the idea, and then we just talk about that instead of stay on the different place. Actually, they are the same calculation, right? So this idea also demonstrate in religion. Okay, religions you think that is very abstract. Okay, Buddhist very abstract, Christian very abstract. They talk about abstract idea, but at first, how this developed? You know how this developed? So Buddha really go into people's society and then see how people suffering, see how they suffer, and then after that he figure out the way. Okay, Christian also, like the Jesus go to every places and then see how people suffer, and then all people sick people, yeah, and then he tells us tell people the way. Okay. So abstract must come from concrete examples. Okay. This is what I want to advocate for abstract. Yes. But of course, if you want to see concrete example, you definitely should point out in the class. Then it's my job to show you. Okay. But sometimes time constraints or sometimes we pass by. Sometimes if you really insist, you should tell me. Okay. Don't wait until evaluation and then write for the evaluation. Say I don't do. Okay. So you definitely should tell me if you want to see more. Okay. Any question up to now? Yeah. So another thing is tomorrow maybe it's a little bit harder. So one thing you need to know is you need to know how to prove something is a subset, subspace, sorry. Yeah, subspace. Okay, maybe I run through subspace a bit. So subspace, okay, I should use this table again. So subspace is a subset of a vector space, which is still a, what am I saying? Subspace is a subset of a vector space, which is still a vector space. Okay. So if you take any two, so you need to make sure 0 is in the subspace. Okay, first of all. And let me use a different. First of all, actually the 0 condition is vector space cannot lie outside your vector space. Okay, this part is not allowed. Okay, have to be in the subset. And then the first condition is 0 vector is inside the subset. Okay. Second is if you take any two floating vector and then you try to add them up. So let me draw it visually. So two vector, if you add them up, it still lie inside your space. Okay. And then it's a bit too small. And then third, if you got an x, when you extend it, okay, let me use another color for this addition. So if you add inside, you still lie inside. And if you scale a vector, it still lie inside. Okay, make sure you know how to show it. And then one thing we get for free from this isomorphism here is there's not really obvious geometry you can see here. But in R3, you can see geometry. In P2, there's not really any geometry here. But in R3, we can draw. Okay, so this is something get from free from this vector space isomorphism. Okay. Yeah. Any question? Any question you want to ask? Any question you want to ask? No. Some admin stuff. So from time to time, I will update the lecture notes. So make sure when you download, you'll see what time it get refreshed because there's a date and time when I upload it, it will record the date and time. So make sure you download the latest one because I will update it from time to time. And then end of this class, we will discuss the quiz from last week. Okay. Okay, so where did we stop last time? Okay, so last time we stopped at eigenvalue, eigenvectors. So today we will develop how to find eigenvalues more effectively. Okay. So let's use an example to help us recall what eigenvalue is. So, should I use this? Okay, maybe I don't want to use this. Let me write it out. Okay, so first example is let's find the eigenvalues of A. 2, 3, 3 minus 6. Okay, so what's the eigenvalue is? So eigenvalue is a lambda that satisfies Ax equals to lambda x. Okay, for non-zero x. Okay, so what does this mean? So this means that A minus lambda I times x equals 0 for non-zero solution x to the null space of A minus lambda I. This is what we have gone through last time. I hope you still remember. Right? I just move this lambda x to the other side. Okay. So the question now is to solve for this homogeneous solution, homogeneous system here. So when is this system have a non-zero solution? Okay. One thing to note here is we only talk about n times n square matrix. Okay. Right. Because why? Because these x should live in the same space. Okay. So this linear transformation should be between the same space. Otherwise, it doesn't make sense. So in an n by n square matrix, when do you have a non-zero solution to homogeneous system? Imagine or not? Try imagine some n by n matrix. So when does 3 by 3 matrix has a non-zero solution to a homogeneous system? Have a row of 0. So you have 3 variables, right? Recall? Can recall? So you need to have a row of 3 variables. So you need to have a 3 variables. So when you have a 3 variable, that means what? Yeah. Also mean what? So the determinant is what? The determinant is 0. So that means the matrix is invertible or not invertible. Okay. So it's not invertible. So the determinant is 0. Okay. So let me put here. C. Okay. So what? So okay. So one condition is determinant of A minus lambda I is 0 since uh, A minus lambda I has this one is throw away, has at least one variable. Right. Okay. So let's use this condition, see if it can help us or not. So what is A minus lambda I in this case? So determinant of A minus lambda I is lambda minus 6 minus lambda 3. Okay, so what's the determinant of this? This is 2 times lambda. 2 minus lambda times minus 6 minus lambda minus 9. Okay, so what do you get for this? This is the thing that will appear to me. What's this? What's this? What's this? Anyone finish calculation? Lambda square plus 4 lambda minus 21. Okay. So can you factorize this? This is lambda minus plus 7 times lambda minus 7 lambda minus 3. Okay. So if you set this determinant equal to 0, what do you find? That determinant of a minus lambda I equals 0, then lambda plus 7 times lambda minus 3 is equal to 0. So lambda is equal to, so what's the root? -7 of 3. Okay. So that means the eigenvalues are -7 and 3. Okay. So what we want to show here is we can use the condition that determinant of A minus lambda is equal to 0 to find our eigenvalue. And then why is this true? Because we want it to be not invertible. This one. So what time is it? 3:37. Okay. So how about try work out this? I give you 5 minutes to work out this. Find the eigenvalues and eigenvector of the matrix. Try and find eigenvectors also, if you have done. Anyone found the eigenvector yet? You like some work to do? Okay. Yeah, let's talk for a while first. Okay. So I forget to tell you the name of this part here. Okay. So when we set determinant of A minus lambda I equals 0, there's a name for this equation. We call it a characteristic equation here. Okay. So a characteristic equation, we call that determinant of A minus lambda I equals 0 is a characteristic equation. Okay. If and only if the lambda here satisfy the condition of being a eigenvalue of a n by n matrix. Okay. So if you satisfy determinant A minus lambda equals 0, then this lambda is the eigenvalue of the matrix. Okay, we call it the determinant of A minus lambda I equals 0, a characteristic equation. It's a character of your matrix. Okay, so I hope we all start with calculating what is the determinant of A minus lambda I. Okay, and then we find the characteristic equation. We set it equal to 0. Okay, so the good thing of introducing this notation here is we don't need to every time say set the determinant equals 0, set the determinant equals 0. We just say the characteristic equation, and then you will know set what thing to 0. Okay. Okay. Yeah. So whenever we say characteristic equation is to set determinant of A minus lambda I equal to 0. Okay. And then from here we should find that the eigenvalues are 5, 5, 3, 1. Okay. So the practice is you write out you write out the roots with multiplicity. Okay, this is a good practice because later we will tell you the reason. So the practice here is to write down all the root with multiplicity. So for example here, L 5 minus lambda appears twice, so 5 appear twice, and then 3 appear once, 1 appear once. Okay. And then anyone managed to finish calculate this eigenvector? Anyone managed to compute the eigenvector? Okay, if not, never mind. You can keep doing at home. I will show you the solution later. But one thing to note here, okay, one thing to see from this raw, this raw reduced form, okay, you can see that A minus 5 has 2 pivot columns. Pivot columns meaning you have 2 free variables. A minus 3i is 1 free variable. And similarly for lambda minus I is 1 free variable. Okay. So 2 variable meaning the dimension of the eigenspace is 2. Yeah, last time we talked about eigenspace, right? Is the null space of A minus lambda I. Did we talk about eigenspace? Yeah, null space of A minus lambda I is the eigenspace because this gives the eigenvectors. So dimension here is 2. So the dimension here is 1, and then the dimension here is 1. Okay, and then you should link this 2, 1, 1 back to this multiplicity here. So L minus 1 is multiplicity 2, and then lambda equals 3, and 1 is multiplicity 1. Okay, so you can see that these two number, this dimension of the eigenspace and the power of the root or the multiplicity of the root match. Okay, but this is not always the case. Okay, so we have this definition here. So we have this definition here. So let's say we have a characteristic polynomial. Okay. So characteristic equation is when this thing equal to 0. So when we just look at determinant of a minus lambda I, we call it a characteristic polynomial. So this is a new word, so I need to highlight. Of the matrix, if lambda minus lambda 0, k divide p lambda, but more than that doesn't divide it, however more than that doesn't divide it, we say that it has the algebraic multiplicity of the eigenvalue lambda 0 equal is k. Okay, so for example, okay, so for example, let me put here. So let me put here. So for example, the algebraic multiplicity for 5 is 2. Okay, and the algebraic multiplicity for 3 and 1 are 1. Okay, so algebraic multiplicity refer to the multiplicity of the root in the characteristic equation. Okay. So when we say multiplicity, then algebraic multiplicity, then definitely there's another thing called geometric multiplicity. Okay, algebra and geometry always come side by side. So geometric multiplicity will be referring to the dimension of the eigenspace of the eigenvalue. Okay. So should I? Okay, let me edit here. So where do I edit? Let me edit somewhere here. We will see it again, but let me tell you first. So definition. Let's now look at this theorem. So the geometry multiplicity and eigenvalue that is defined to be the dimension of its eigenspace, or the dimension of the null space of A minus lambda I is the same. So you swap between eigenspace and null space of A minus lambda I. Okay, for null space A minus lambda. Okay, these two are the same thing, but this one will tell you how to compute it. Null space of A minus lambda. So the conclusion we make in the previous example is we see that we see that the algebraic multiplicity just with geometric we see that every algebraic multiplicity matches of an eigenvalue. We see that every algebraic multiplicity of eigenvalue matches with the geometric multiplicity of eigenvalues. Let me box this guy. Okay. But we will later see again this thing happening. So we can deduce something from this. But this is just a observation for now. we see that there are two numbers are equal. Okay. Then later we'll see what does this imply. Okay. Also from this example here, right? Okay. You can also see that last time we end with the lecture of this one of this theorem. The eigenvalues of a triangular matrix is the entries of the main diagonal. Okay. So just now from that example, this now is a triangular matrix. So you take minus lambda, and then when you take the determinant, actually it just appear at the diagonal. Okay. So when you set equals 0, then you really find the eigenvalues from the diagonal entries. Make sense? Okay. So in the textbook, they produce a proof for 3x3 cases. So you need to imagine for n by n cases. Or you can write it down. Okay, so we do this. We do this quickly. Do this. Okay, so quickly do this. So characteristic polynomial of a 6x6 matrix is this. This polynomial here you already given. Okay, so does it make sense that why you have lambda squared lambda to the 6 here? Does it make sense why? Why the power here is lambda to the 6? Hmm? Why the power is lambda to the 6? What's the size of the matrix? 6. Okay. So when you multiply 6 factors together, you get the power lambda to be 6. Okay. So that's why this lambda to the 6 appear here. Okay. Okay. So what's the eigenvalue? So you need to consider the characteristic equation. Okay. I think I've spelled it wrong. Characteristic equation. Okay, you set the determinant equals 0, so lambda 6 equals to 0. Okay, so how you factorize it? So lambda square, lambda, okay, actually you can take 4 of them out. Lambda 4 times lambda square minus 4 lambda plus 12. So can you factorize further? Lambda minus 6, lambda minus 2. Okay, so what's the root? So the roots are 0, 0, 0, 0, and 6 and 2. Okay. Or you can say that lambda equals 0 with multiplicity. Let me try some. Yeah. What? Plus 2? Okay, sorry. Plus 2. And then this one is minus 2. Okay. So, okay. So the other way you can say is lambda 0 with multiplicity 4, and then lambda equals to 6 with multiplicity and lambda equals to minus 2 with multiplicity equal to 1. Or actually we will split these three out, so we will say L lambda 1, lambda 2, and lambda 3. Okay. There are few ways to talk about it, but yeah. Depend on what people want, then you can say it more clearly. So if they want, if they ask for eigenvalues and their multiplicity, then maybe better to write this way. If they only ask for eigenvalues, maybe you can write this way. Okay. See which one is more clear. Okay. Mm. Let me see. How about, let me see. How about we finish a proof first before we take a break? Okay. Let's torture first and then we take a rest. Okay. Okay, so next theorem. Okay, actually I was thinking want to prove this theorem or not, but it seems that we will use this theorem, so maybe we prove it. And because it's not too hard, so hopefully everyone can see it. Okay, let me explain first, then we will prove this. Because later we will use this fact. Okay, let's start with V1, V2 up to Vr, okay, which they are eigenvectors. And for all of them, they are correspond to different eigenvalues, okay? Meaning, if you take matrix A, you add on V1, you get lambda V1. You add on V2, you get lambda V2. Lambda 1 and lambda 2 are different. And then you get lambda 3. Lambda 3 are different from lambda 1 and lambda 2, and then so on. Then, okay, then the set of V1 up to Vr are linearly independent. Okay, last time we talked about this is a new source of basis. New source of basis. Okay, so why are they independent then? So it's very important, right? You said they form a basis. So why are they linearly independent? Okay, so uh, the usual trick is see if I can fit it here. Maybe we use 3-step finish the proof. See, challenge, 3-step challenge. Okay, so proof. So they say it is linearly independent. I don't believe. So suppose it is not. Okay. So suppose it is not. Suppose it is not. Okay. Then there exists non-trivial solution, right? To the what equation? Still anyone still remember what equation is that? Such that C1 V1 plus C2 V2 plus C3 V3 plus dot 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 plus C R VR is equal to 0. Okay, so there's a non-trivial solution to this equation here. So what can you do next? Actually, there's limited thing you can do, but there's one obvious thing you can do. You know what you can do? Uh-huh. Can you do? What can you do? Seems like if you apply A, you got nothing to do with it. What can you do? I was thinking I never see you before. Wait, what can we do? Eigenvector. What can we do? What can we do? Eigenvector. Yeah. What can we do? Eigenvector. Huh? What can we do? Huh? Can you apply A on both sides? Yeah, let's call this a matrix A. There's no name for this matrix, call your name A. Okay. So apply on both sides, right? Can you apply on both sides? Just apply on both sides. A times both sides. All right. Okay. So what do you do? What do you get? What you get is C1 lambda 1 V1 plus C2 lambda 2 V2 plus C3 lambda 3 V3 plus blah, blah, blah. Okay. This is what we get, right? Okay. But seems not very helpful. Not very helpful. Too many information here. So you can see that this guy here is almost the same as this guy. Right? Just some number multiply V1. Okay. So how? How? Too many things here. So how? So how? Okay. So so I think we need to throw something out. Okay. So how to throw something out? Meaning let's pick the smallest k less than equal to r such that C1 V1 plus C2 V2 E3 V3 plus plus until CK VK minus 1. Okay, CK minus 1, VK minus 1. Okay, so let's throw some guys up. Okay, because it's non-trivial solution, right? So that means there's some zero, some non-zero, some zero, some non-zero. Okay, so I throw all the zero at the back up. Okay, make sense? Does that make sense? Okay, so for example, okay, for example, let's say C1 is 0 and V1 plus 1 times V2 plus 2 times V3 plus, for example, 3 times V4 plus maybe 0 times V5 and all the way up to 0 times VR, right? So that means when I set this equal to 0, right? So I can just take V4 equals to uh, equals to what? V4 equals to minus V2 minus 2V3 over 3. Like this. Okay. Does it make sense? Make sense? Make sense? So I pick the smallest such that I can write this guy in terms of the rest below it. Okay. Because all here all zero already. Okay. This one doesn't matter. But here matters. I can write V4 as this. Make sense? Okay. Okay. So now this one will be a little bit more helpful because when you add on A again, okay, let's add on this guy again. So if I add on this guy on A again, what do I get? I get the same thing actually. So I get C1 lambda 1 V1 plus C2 lambda 2 V2 plus C3 lambda 3 V3 all the way up to k minus 1 lambda k minus 1 dk minus 1. Okay, equals to lambda k vk. Okay. So how? So how? So how? We got this. Okay. We also got this. Can we play something or two things? Okay. Can we do? We have learned so many substitution, right? So how to substitute? They both have a LVK here. So how to substitute? Can substitute or not? Can you do? Huh? So we can multiply lambda k to this line, right? So we multiply lambda k to this line. Okay. And then I take the first one minus the second one. Okay. So first minus second, what do you get? C1 lambda 1 minus lambda k B1 plus C2 lambda 1 minus lambda k V2, and then so on. Ck minus 1 lambda k minus 1 minus lambda k Bk minus 1. So what's this? So what's this? Yes, yes. So since by assumption lambda I not equal to lambda j, because they are all distinct, distinct, and C1 must be equal to C2. Okay, for the okay. Right. So our condition here, distinct is a distinct eigenvalue. So the difference here must be non-zero. Okay. So for it to be zero, all the coefficients C1 to Cn must be zero. Okay. If it is not zero, then contradiction. Okay. Yeah. Any question? Okay, let's take a break first until 4:22 and then come back.啊，要。我直接开。哦，这个不用发。哎，这个可以发，actually。到底多少？时间。等一下再发这个。这个等一下，等一下，等下我怕等下来不，等下人没有在，没有签的。啊。OK。这个就是我那里看的，然后呢，为什么它就硬坑人？这应该是。对，这个是 independent，actually，我写错。其实。为什么？哎，你 dependent 我是说。 对对 dependent 没有错。啊，因为我用把了，应该是要，哎，因为我干嘛？哦，也对对，然后
这部分段没看懂在干嘛，这个有点乱。
这个在那个，我看看。OK，
一个正 at most，一个正 at least。
对，没有错。
后半段正 at least。正这个的。
对。
然后就看不懂了。这个
OK，
你假设它的m 比 n 小，
对，
这一段
神奇，这个应该是关键神奇。你说，
我就没看懂它这个二，就是
如果假设这个 B2有少于 n 的东西，对不对？所以你这边有 m row 和 n column，对吗
？m 乘
？m 乘 n，
matrix。
对
对，然后呢
m row 和 n 的 column 嘛，对不对？所以如果你的 m 比较小，你的 m 比较大的话，那你的 pivot 有几个？
这个是列是 n 个
因为你有 n 个东西要用 m 个东西来表。
东西，我用 m 个东西表达，能不能表达出来？
可以表达出来，只是说表达出来过后会有这个 non-trivial 少。OK，你现在是有 V1、V2到 Vn，对不对？但是你这里有，比如说 B1到 Bm 啊，
m 小于 n 必须有一列。
对，
那个
对，
没有 pivot，所以它就是
yes，
然后还有这两页我也没 get 到什么意思，就好神奇，我感觉。
OK，这个 dimension 会吗？
对 dimension 会。
这个 dimension 会。
对。
好，
然后
其实你要懂的就是这个吧。
你写的话我就看不懂了，然后这个好抽。
对，这个抽象就是，对，你先懂这个先，OK，
对。
懂了这个过后，我想说的就是，其实这里你看，就刚才我在课堂上面又有补充，就是说，你看这个 Rn 跟这个 Pn 代表同一个 n，但是他们两个是不一样的。对，就是要说这件事情。
所以你现在发扬言就是说，有可能是代表同一个东西，但是它俩是代表不相同。
对，比如说这个一是这一只，一是这一只，但这两只不一样。
它俩但是两个不是一样。哎，
可以这样讲，可以这样讲，可以这样讲。
没看到是什么？
没看到。对，继续你懂。然后你知道这些，你知道这一个是 R3 的 subset 吗？你知道哈？OK，然后现在你要说的是它是不是一个 subspace 啊？从你的答案看来，然后你是说为什么这个东西是在 R3 里面，还是这个东西？嗯，
因为不懂这个怎么体现三个零的反面。
你知道他们这些东西全部在 R3 里面，你知道哈？他的意思是说这一个 vector 不活在这里面，就是你不能够用这里的来表示它，因为这里的所有的 vector 肯定是中间有一个4，你是不能够把这个4去掉啊。所以，但是这一个就不能够用这个有一个4的来表达，可以吗？所以这个其实还有一个比较深的东西，就是 你可以看到这个不是，它不能够写成 span of 一些 vector。通常如果可以写成 span of 一些 vector 的话，就是它是一个 subspace。它就是因为这个零的原因，就是你也不能够在四旁边乘任意的 scalar，也不可以，也不可以的啊。你可以变的只有上面一层跟下面一层的，可以理解吗
可以。
？OK，好笨。Let me ask this attendant. Actually, right, when you, at least for me, I think it's normal you feel like lost in mathematics. Because even for me, right, okay, my first year, right, after the first, I think, first 15 minutes, after first 15 minutes, I was lost. Literally every lesson, I was lost after 15 minutes. I try very hard to understand, but I really lost after 15 minutes. And then second year, I get better. After 30 minutes, I lost every lesson. After 30 minutes, I lost. And then third year, I get better. After 45 minutes, and then I lost. Surely after 45 minutes, I lost. Yeah, so, and then after that, 1 hour, I can listen to 1 hour things and 2 hour things. Yeah. So why, I think about why I lost, okay? Because when those people talking about something, right, eh, if you are not imagining what that people are doing, you will lost because you don't know what he is doing. Okay. But so when I say about something, right, try in your mind, imagine something. Either is correct or wrong, just imagine first. Okay. Try to practice to put something in your mind. either wrong or correct, that's fine. Just try to imagine something. Okay, try to form some image in your mind. Yeah. Okay, but I will try my best to put some image in your mind. Okay. Okay. So so let's do this just by inspection. Okay. Let's do this by inspection. Okay. So for A, B, C, D, okay, can you immediately tell me what are their eigenvalue? For A, what's the eigenvalue? Can you see what's the yeah, what's the eigenvalue is? What's the eigenvalue for A? So for 3, right? Because okay, I want you quickly form this calculation in your mind. Quickly practice and form this calculation. So a theorem says that the diagonal entries in a triangular matrix is the uh, eigenvalues. The other way to see is if you take A minus lambda I, okay? So you take A minus lambda I meaning you minus lambda on the diagonal, and then you take the determinant, okay? And then set it equal to 0. You look at the characteristic polynomial. So when you say to 0, so what are the roots? The roots are exactly lying on the diagonal entry. Okay. So we only do the exercise once, but you need to go back and practice this exercise. Okay. Practice, you need to write down the whole step at home, not here. Okay. So B, what's the eigenvector? This is also a triangle matrix. So triangle matrix, the eigenvectors lie on the diagonal. So the eigenvalue is 4. Okay. Yeah. So yeah, of course, but the what? But the definition of the characteristic equation is if lambda satisfies this polynomial here. So just now the polynomial should be 4 minus lambda, x minus lambda, 3 minus lambda equals 0, right? So if you put lambda equals 0, it doesn't satisfy the characteristic equation. So only when you are the root of this characteristic equation, you are the eigenvalue. Okay, root of the, so let me write down. So eigenvalues are of A are the roots of characteristic equation. Okay, so eigenvalues of A are the roots of the characteristic equation. Okay, if for triangular matrix case, the diagonal entries are the eigenvalues. Okay, similarly for C, lambda equals to 3, 3, 3. D is 3, 3, 3. Okay, so you can see that these two are the same, these two have the same eigenvalue. So why we put this example up? So there must be a difference between AB and CD. Okay, so you can see that the difference here is I have a 1 here, I have a 1. So I have no, so this is a triangle, this is a diagonal matrix, but I have a 1 on the off diagonal term, but for C and D, we have 1 on the off diagonal term and 2 ones on the off diagonal term. Okay, but if you do row reduction, if you are familiar with row reduction, you will know that this one will affect your dimension. Okay, so for example, let's look at a minus 3i. Okay, what is a minus 3i here? So a minus 3i here should look like 4, 0, 0, 0, 0, 0, 0, 0, 0. Okay, how about a minus 3i here? Okay, here is 4, 0, 0, 0, 0, 1, 0, 0, 0. Right? Is it? Oh, sorry, 1, 0, 0. Yeah. Okay, good. Right? Huh? Oh, first is 1 also. Okay, good. Okay, good. So you can see that the dimension of the null space change. Okay. So first one, what's the dimension of the null space? Huh? You sure what? What's the dimension of an eigenspace here? 2. Because you have 2 free variables. So what about what's the dimension of the null space of B minus 3i? How many pivots you have? 2. So what's the dimension of the eigenspace? Huh? Huh? 1. Right? Okay. So you can see that the algebraic multiplicity here is not equal to the geometric multiplicity here. Okay. In the second case, they are not equal. In the first case, they are equal. Okay. So it could happen that the geometric multiplicity is less than geometric multiplicity less than the algebraic multiplicity. But geometry will never be more than algebraic multiplicity. Okay. It's always less than or equal to. Okay. So we keep remembering this principle here. Geometry multiplicity is less than or equal to the algebraic multiplicity. Okay. Yeah. We still don't review what is going to do with these two things first, but remember this principle, then later we will see again. So you will go back and see that these two also are the same. Okay. The geometric multiplicity is less than the algebraic multiplicity. And then see how it affects this diagonal here. You can see this relation. I won't tell you, but see what happened to the diagonal. How the matrix is close to a diagonal matrix. How close is a matrix to a diagonal matrix? So for A, this is really a diagonal already. But this one have extra 1. And this one have extra 2 ones. Okay, I won't tell you what's going on, but try and see what's the connection between diagonal and geometric multiplicity and algebraic multiplicity. What's the relation between this and diagonal matrix? Okay. Okay. Okay, next, the next concept we want to touch on is similarity. So people keep asking me, is AB equals to BA? AB a matrix. So is matrix multiplication commutative? No. You can give simple example. What simple example? Just pick something like this. Okay, then it is not true. Is this true? I hope this is not. Maybe change it. You just create any two. They will be not commutative. Okay. So so this is the part that matrix doesn't look like number. Okay. Number when you multiply 2 times 3, 3 times 2 are the same. But matrix is not. Okay. So this means matrix contain more string, more information than numbers already. Okay. But there's a thing. When we say A and B are similar, if there's an invertible matrix such that A equals to P times B times P minus 1. Okay, this one is really close to what we're talking about before. Because if you multiply P on both sides, we'll get AP equals to PB. Okay. So AP, when you swap, A becomes B. Okay, there's another thing, there's another matrix that replaces A. Okay, AP equals to PB. Okay, if P is invertible, then we can move the P to the other side. Okay. Or sometimes we will say, in group theory, we will say A is conjugate to B. So you conjugate PP minus 1 on both sides. Okay. Conjugate. Sometimes we say conjugate. But for now, you can memorize this similar. So if A and B are similar, if there exists a invertible P such that A equals to PB P minus 1, P to inverse of P. Okay. Or in other words, AP equals to PB. Okay. So there's a B that replaces A. So why are we interested in this guy here? Okay. So let's say two matrices are similar. So two matrices are similar. We have A equals to PB P minus 1. Okay. Then they have the same characteristic polynomial. Okay. So can we see why? They are the same characteristic polynomial. So if we want to show that they have the same characteristic polynomial, then we need to compute. Okay. So let's compute what is determinant of A minus lambda I. Okay. So what's the determinant of A minus lambda I? Is equal to the determinant of PB P inverse minus lambda I. Okay. Right. Okay. So what trick we can play here? We can introduce PP inverse on the other side also. Because P times P inverse is identity. Okay. Then what can we do? We can factorize P and P inverse on different side. Right? Okay. So we factorize P e minus 1 minus lambda I e minus 1. Okay. And then we factorize on the other side P inverse. Inverse. Everyone agree on this factorization? Agree? So P I factorize out. P inverse factorize on the right. Is it okay? Okay. 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 So what's this? Determinant of P times determinant of B minus lambda I times determinant of P minus 1. Okay, this one is by determinant of AB equals to determinant of A times determinant of B, because determinant is multiplicative. Okay. So what is determinant of P inverse? Anyone remember? Did we discuss this formula before? Determinant of A P inverse is 1 over determinant of P. Discuss this before? Okay, yeah, okay. So you got determinant P and 1 over determinant P. So you can cancel. Okay, then you get determinant of B minus lambda. Okay, so we get that determinant of A minus lambda I and determinant of B minus lambda I is the same. Okay. Yeah. Okay, so maybe you think why so troublesome we want to do this. Actually, it has a very good application. Soon we will see. Okay. Yeah. You think that maybe you think there's very much more work here, right? You want P inverse some more. Okay. I only got A. Do deal with one A is enough. Okay. But later we'll see that when B is diagonal, this is very useful. When B is diagonal, this is very useful. Okay. Then we will go into the next part, which is the diagonalization. Okay. Let's show you how useful is diagonal matrix first. I think we roughly talked about this last time, right? When we talked about matrix multiplication. So let's say we got a D as a diagonal matrix with diagonal entries 2 and minus 3. So what is 2 squared? Anyone know what is 2 squared? It's D squared. What is D squared? Squared. 4, 0, 0, 9. Okay. How about cube? What's D cube? 8, 0, 0, 9. So you can really see that if you want to do matrix, take power of the matrix, what you do is really you take the power of the diagonal entries. Okay. So this make matrix multiplication easier. You don't need to do column, row, column, row, column, column. Okay. You just take product of diagonal entries. Okay, good. Then how about this one? You make this one smaller. So how about this one? So D is a diagonal matrix. P is something weird. Okay. And then we let A to be this guy here. Okay, I let you try for 5 minutes. Try and compute A square and A cube. Okay, let you try. What is A square and A cube? I let you try. The first one who finish, you can tell me what is it. A square and A cube. So A is the thing equals to P inverse. Okay. So now compute A square and A cube. The first one who get it, you can tell me what is A square and A cube. Zhao Ling not here today. Zhao Ling. Yeah. Zhao Ling not here. You haven't got yet. for x squared. 2. Huh? Just for 8. Oh, what is a square? I mean, what is a square? 400. I think something wrong. 400. 0. Oh, 9. This one. A cube. I think a square is not right. Seems like a square is not right. Oh, wait. Okay, maybe it's right. Okay, maybe it's right. I'm not sure. How about a cube? You got it? Okay. Great. Okay. So can you tell us how you got it? So you get P inverse first, and then you multiply these three together, and then you multiply. Hey, so you go the hard way, okay? So the hard way is you get the P inverse first. Okay, so what's your P inverse? If I'm not wrong, it's 2 minus 1, 1 minus 2, I minus 1. Is it? Is this? Okay. So you get the P inverse, and then you compute A, then compute. Okay. But actually there's an easier way here. Okay. Direct. What do you mean by direct? Okay, let me say. So okay, so this is a hard way. So this is a hard way. So there's an easier way. So now the easier way is theory. So why this theory work? Okay. So the theory is if you take a square, okay, I don't need to care what is p and d first. Okay, I'm multiplying p dp inverse and p dp inverse. Okay, but by associativity, we can multiply the middle two matrix first. In this case, what do we get? We get PD identity D P inverse, which is P D squared P inverse. Okay, so we actually bring the power all the way into the diagonal matrix. And we know how to take the diagonal matrix, the power of diagonal matrix, which is just the power of diagonal terms. Okay, so this is the power of this conjugation. So instead of multiplying this A here, can you tell what is A actually? A is what? 2003. 2003. Oh, in this case it's also easy. This is just diagonal matrix. Is it? Okay, never mind. But let's say this is not diagonal, then this product here will become very hard. Okay. Does everyone got this A? Same A? Okay. So if this is not diagonal, then this will be an easier way. Okay, so you can take P times the power of the diagonal and then multiply by P inverse to get the power of A. Okay, so in general, AK equals to P D to the power K inverse. Okay. Okay. Yeah. So you don't need to take P K times or P inverse K times. Okay, or the mixture of them. So all the middle term will cancel. Okay. P inverse P and then P inverse will get along with another P. P inverse will get along with another P. Can run it? Can see? So for example, I let you see A3. So A3, what do we have? PD, P inverse, PD, P inverse, PD, P inverse. So you keep repeating P inverse P, P inverse P, like that. Okay. So all the middle P inverse and P will combine into identity, and then you left with diagonal matrix. Okay? Is that okay? Any question? Does it make sense? Sense? So this is equal to PDQ P inverse. Huh? Just ask if you got any question. Yeah. Okay. Let's say we want to find A inverse, right? So A inverse is what? I think it's model. So if we want to find A inverse, so inverse of A is equal to PD P inverse inverse, which is equal to how do you take inverse? So what is inverse of AB? Inverse of AB is what? B inverse times A inverse. Okay. So you get E inverse, inverse, D inverse, and inverse. Okay. Inverse, inverse, you get P, D inverse, and inverse. Okay. So that's mean if you take A inverse of P, D, P inverse, so then you will get P and P inverse swap, and then you compute inverse of D. Inverse of D, you just compute you just take the inverse of every entry. So for example, if you want to take inverse of 2, 3 here, is what? It's just 1, 2, and okay. Because when you multiply these two matrix, you get identity. Right? You multiply row and column, row and column, and then row and column, and row. Okay. Suitable for all matrix. We mean which one? You mean this or this example here? No, this one is just for diagonal. Only for taking diagonal. So yeah. So the inverse of the diagonal matrix is also easy to find. It's just the inverse, taking inverse on every diagonal entry. Yeah. So taking power also, power of diagonal matrix is just taking power of diagonal entries. So diagonal matrix really works like number. Think about it. Diagonal matrix really works like a number. Say, yeah. Let me write something. Let me write something. Diagonal matrices look like numbers. Okay, but with a lot of numbers considered together. Okay, so for example, if you multiply two diagonal matrix, right, you can just commute them. Okay, and then if you take the inverse, is just taking inverse on the diagonal term. What else want to add? Oh, and then if you take power, it's also taking power on diagonal. This one doesn't work for general matrix, but diagonal matrix works. Okay. Okay, the next part is we say that a matrix is diagonalizable if it is similar to a diagonal matrix D. Or we write A equals to PD P inverse for some invertible matrix. So if uh if so if AP equals to PB, where B is diagonal, then A is called A is diagonalizable. So that means you apply a P, you use a P to make A into a diagonal matrix. Okay, so we say A is diagonalizable. Okay. Okay. Yeah. Any objection? No. Okay. So let's look at this one. Should we? Maybe not. Oh, maybe yes. Okay. Look at this one. Okay. So let D is the same example just now, but let's say we want to find the eigenvalues and eigenvector of A. Okay. So what have we learned? Okay. When we say that two similar matrix has the same eigenvalue. Okay. But in this case here, A and D are similar. So A has the same eigenvalue as D. Okay. So let me write down. Since A and D are similar, then A and D has the same characteristic polynomial, have the same characteristic polynomial. In particular, they have the same eigenvalue. Okay. So why is it good? So if P, A and D has the same eigenvalue, D is diagonal, D is triangular. Okay. So you can read the eigenvalue from the diagonal entry of D. Okay. So in this case, what's the eigenvalue? The eigenvalue is what's the diagonal entry of D? Is 2n minus 3. Okay. So 2n minus 3 is the eigenvalues of the A. Okay. How about eigenvectors of A? Okay, let's work out this. Okay, this one is quite important. Maybe let us work out this. So just now what do we have? Let's compute this one. So let's put this. So just now we got that A is what? A is just, what do we got for A just now? 2 and 3. Do we get this 2003 for A? Is this right? I got some doubt. Wait, let me compute. P inverse is what? P inverse is 1 over determinant of A, 5 minus 6 times minus 5 and minus 1 swap, and then minus 2 minus 3. Okay, remember for this? Okay, let me do some calculation. So 5, 3, 2, 1. Yeah, this is P inverse. Is this what P inverse we got just now? Why different one? Okay, I think this is right? Because AD minus BC, AD minus BC, okay, minus BC. So 6. 5 minus 6 is minus 1. And then so 2 by 2 matrix, you swap A and D, right? And then you put minus on B and C. Okay, so this is P inverse. So let's compute what is A. A equals to minus 1, 2, 3, minus 5 times the diagonal, and then times the inverse. Okay, let's get what's this. So what's this? Minus 2, and then the 6, 15 times 5, 2, 3, 1. What do we get? Minus 10, minus 18, minus 28. Please help me to check. Wrong. Minus 4, minus 6, minus 10. 6, 30, 30, 30, 45, 75. So big. 12 plus 15, 27. Is this right? Yes, right. Okay, good. Okay, so let's see what is the eigenvectors. So eigenvectors. So we have two eigenvectors, lambda equals to 2 and lambda equals to minus 3, right? So let's find the eigenvector, which is to find the null space of A minus 2i. Okay, what is A minus 2i? A minus 2i is minus 30 and 25, minus 10, and then 75. Okay. So row reduce this. This is like a pain. You have to do it fast. Okay, let's do 20, divide by 25 on row 2. Okay, I get minus 10, and maybe make it easier, divide by minus 10 on row 1. So I get minus, so I get 3, 1, and 3, 1. Is it? Yes. Yeah. Okay. What? It's not magic, it's just dividing by 1 over 25 and divide by 110. Right? Agree? Okay. So this one will turn into 3100, obviously. So what's the now? What's the solution? What's the parametric solution here? So it's S2 time minus 1 over 3, 0. Right? Wait, sorry. 1. Because S2 is free. Okay. Yeah. Okay. How about A minus 3i? So A plus 3i, what do you get? So you get minus 25, 30, minus 10, 75. Okay, again, large number. What to do? Okay, divide by their GCD. First divide by minus 5. Second divide by GCD is 15. No, 15. R2. So first you get 5, 2, and then second you get 5, 3. Right? Okay. So this is raw equivalent to 2. Okay, 5, 2 again. Okay. Yeah. Okay, this one makes sense. So 5, 2, 0, 0. So let's make some space. Precise. 525. Okay, so what's the solution here? What's the parametric solution here? So you get S2 equals to minus 2 over 5, 1. Okay. Okay. So uh so what? So what? So these are the eigenvector. So maybe we can do some magic here. I don't like vector with fraction. I don't like vector with fraction. So I can make this eigenvector, since it says that anything times this will be my eigenvectors. Why not I choose a better one, better looking one? Okay, so I can choose a nicer vector. Okay, or nicer eigenvector for lambda equals to 2, which is, which one I want to pick? I want to pick, I multiply 3 of both, so I get minus 3, minus 1, 3. Okay, right? Because anything times this vector would be my eigen vector, so I just take x2 equals to 3. Okay. Similarly, we can choose a nicer eigenvector for lambda equals to e to minus 3. So eigenvector for lambda equals to minus 3. Which one can we pick? Maybe this time I multiply by minus 5, which is 2 and minus 5. Okay. Do you agree that I can multiply any scalar? Can, right? Okay, because this is. And then what do I get? I get minus 3, minus 1, 3. 2 minus 5. I'm being a little bit small. So let me write something somewhere here. So for lambda equals to 2, I found the eigenvector v lambda, again, let's put lambda 1, is equal to minus 1, 3. And then for lambda 2 equals to minus 3, I get v lambda 2 equals to 2 minus 5. Okay. So do you notice anything? Do you notice anything? Huh? Vanya, you see anything? Forms the corner of P. So the column of P is actually the eigenvector of your matrix. So you might at first you think that I need to find a random P, make my matrix diagonal, but actually the thing that make your matrix diagonal is the eigenvector. Okay. So how to look? So whenever you want to diagonalize a matrix, first you need to look for the eigenvalues, look for the eigenvectors, and then form the matrix P using the eigenvectors. Okay. So the theorem, what we did is the theorem. So the theorem says that an n by n matrix A is diagonalizable if and only if it has n by n linearly independent eigenvectors. And then this will form the P matrix. Okay. So form matrix P using n linearly independent eigenvectors. Okay, maybe we don't prove this today. Not sure we want to prove it or not. Let's leave it because we already seen an example. And then the next thing is an n by n matrix A with n distinct eigenvalues is diagonalizable. Because just now we proved that a matrix have n distinct eigenvalue has n linearly independent vectors. And then if you have n linearly independent vectors, you form a P and then make your A diagonalizable. Okay, diagonalize your A. Okay, so an n by n matrix with n distinct eigenvalues is diagonalizable. Okay. So, what time is it? Okay. Any question up to here? Question? Huh? Take a break. I think the next break we take is until we will discuss quiz. So we finish what we need to finish today first, and then we take a break. Is it okay? Okay, let's do one last thing. Okay, try use the technique just now and diagonalize this matrix here. This one. Yeah, do this one. Those I don't discuss in class, right? Left as exercise, then I will produce a solution to check later. So now we do in class, diagonalize this one. Okay, this is the last thing we do before we discuss quiz. So first, go and find your eigenvalue first, and then find eigenvector. Use eigenvector, form the P matrix. Okay, see whoever got it first, tell me what's the P matrix. Is it hard to compute? Okay, maybe I give you some hint straight away. I give you this characteristic polynomial, and then get the get the get the root from here. Try start calculate the vector. Anyone found vector? Anyone found vectors? Anyone found eigenvector? But the problem now here is, no matter how you find, you only can find two. You see it? What's the dimension of the eigenspace of dimension of null space of A minus I? What's the dimension of A minus I? One. Okay. What's the dimension of the null space of A minus A plus 2I? How many people here? Okay. So you can only found two vector here, no matter how you find. But you need how many vector to make P here? This is a 3 by 3 matrix. So your P is also 3 by 3. So you need 3 vectors. So you only have 2 now. So you can never form P. This means what? So this means A is not diagonalizable. Diagonalizable. Since it has only two linearly independent eigenvector. Okay. So return to the theorem again. Okay, the theorem saying an n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Okay. So you don't have enough, it is not diagonalizable. So also you can see what? The algebraic multiplicity of -2 is what? Is 2. But the dimension, the geometric multiplicity is 1. Okay, so this means we have a theorem. So if the dimension of the eigenspace of the eigenvalue is less than or equal, okay, this one is always true, less than or equal to algebraic multiplicity of itself. Okay, and A is diagonalizable if and only if the geometric multiplicity of each eigenvalue equal to its algebraic multiplicity. Okay. So you must achieve the algebraic multiplicity geometrically so that you are diagonalizable. Okay. Otherwise, you don't have enough vector to form P. Make sense? Okay. Okay, there's one more thing I didn't tell you, but I'm not sure you noticed or not, right? So how you place this 2 and -3? Can you simply place, can I place -3, 2 here? Okay. So these 2 and -3, right, correspond to the number of column of your column vectors. Okay. Could correspond to the position of the column. Okay. For example, -1, 3 is the eigenvector for 2. So first column is 2. Second column -3. Second column is the eigenvector for lambda -3. Okay, so correspond to the eigenvector you place. Okay, yeah. This is another thing. Okay, so the other can left as exercise. So so we will take a break until 5:29, but in the meantime you can come and collect your quiz one by one. Okay, don't squeeze down here. So take one by one you can. And after then we will discuss at 5:29. Attendance, where is the attendance? Okay.
对，我现在可是一节都不敢露签呀。
Okay. Please sign your attendance if you haven't. And can't get your quiz one by one. I
这个，我跟他说，
成两条高。对。
就是它有一个 pivot position 的意思，就是它只有两个是
没有，它这个 eigenvector 是这个的 null space，所以你要算它的 free variable 嘛。
independent。
哦，刚才我们不是有证了，如果它是不同的，它不同的 eigen values 来的 eigenvector 肯定是 linearly independent。对啊，刚才我们有花一个时间这样子证。
这个我也没看懂。
对，这个就是说，这个简单，它就是说，它简单来说就是，如果你有 v1到 v2，但是它们都是不同的 eigenvalue，它们的那个 vector 肯定是 linearly independent。从地方来的 eigenvector 都 linearly independent。对，
我直接等，可以，
就是说我选，比如说这个例子嘛，你看，如果我有这个东西啊，我选一个最小的 k，such that 我可以把这一个写成剩下的东西。
是我的意思是说，如果我根据这个，我就跟，假如说我根据这个，我把这个放到右边来的话，我不应该。
因为啊，假设如果 CR 是零的话，你就不会这么做。要 CR 不为零的时候，你才可以。
就现在先要归零，然后我做这个的意思
一样的，你做这个意思，就是因为等一下我们会制造出两个 equation 来比较，因为之前我们只有一个 equation 没有的比较，所以现在如果我把 vk 搬过来过后，我就可以有两个 equation 来比较。
我只不过是把 vk 前面的所有项都写成 vk 的形式
对
而已，然后让这个就是方便计算这个。
对，那我们就可以呀。
然后，对，所以说我这个算到最后，我找的是那个，是那个 pivot position 的那个 non space，也就是说，就是它那个找它那个
free variable，对，null space，对，null space，
为什么这个 full variable 就是它那个，
null space，
对，就是它那个 non space 就是它的那个，
null space 哦，记得怎么找 null space。
我知道怎么找 non space。
因为如果你有一个 null space，如果你符合这个条件的话，你是符合这个条件，记得吗？所以那个不只是往这里到上面，它也可以往下面上来，所以这是下的 equivalent 的 condition。你解这个也是等于在解这个
这个
啊，这个是 eigenvector 嘛，对不对？eigenvector 是一个 vector such that AB 等于 lambda b 啊
对啊，就是这个跟这个不是相等的吗？
相等哦。所以我解了它 null space，我就解了这个 eigenvector。
在解 non space 了，所以说我所以我找到了它的 不是它的那个
dimension。对。
不知道说那个 determinant，
对对，
那是指就是这个不打算没有任何简便的。
你或者你要用那个什么先把它，可是如果 reduce 又很麻烦，因为它有减 lambda，对不对？
对，
不能哦，你只能够用 core factor，应该是最快的。
所以就是只能这么长。然后，就是他给的这个这个第四，那这个 D 是怎么给的？
哦，就是你要我刚才说那个你要配，比如说刚才这个 example，你看你这个号这个第一个 column 的东西，你一定要配去它的 eigenvector，就是第一个 column 的这个第一个 diagonal 要配去第一个的 vector eigenvector，它自己的 eigenvector，懂什么意思？就是你看二是 eigenvalue，它的 eigenvector 是减一升，所以第一行你要配去第一行第一个的 diagonal 要配去第一个，可能第二个。如果我把这两个交换，这样这两个也交换。Yeah, take a photo of your 硬件然后来。哦，OK，要录那边。Yeah, take a photo of your please. Thanks for returning. Okay, before we discuss, I want to acknowledge some of you because you did a great improvement. For example, Bo Kai, Yang Bo Kai, Yang Bo Kai, yes. Bo Kai is here. Yeah, Bo Kai got great improvement from 5 to 15. Very good. And then who else? Ao Jing also. Ao Jing straight away from 4 until 20 full marks. keep the good work. Keep the good work. Okay. 叶大为 who is 叶大为？叶大为。Let me see who are you? Okay. Yeah, very good. Also have some improvement. 孟兆林 also. 齐玉俊 齐玉俊啊，齐玉俊 is 齐玉俊 here? 玉俊 not here. 张俊豪 yeah, 张俊豪 yeah, very good. Johnny also a slight improvement. Johnny. Okay, let's start. Let's start discussing. So we got Injie solution here again. Okay, so first question is finding inverse. So remind you tomorrow still have question finding inverse. So make sure you know. So find the inverse of A by using elementary row operation. So what does this mean? This means that you need to set up, you can set up an AI augmented matrix, okay? And then row reduce the left and row reduce the right, and then the right will give you the inverse. So this is a convenient way to write. Let me write this down first, and then let me tell you. So if you row reduce your matrix identity, okay, then you can multiply everything on the right. So this thing here basically is your inverse. So en how to I are basically your inverse. Okay. So if you apply it on identity, you will straight away get your inverse. What the augmented matrix doing? I think not many not many people have problem on this, so it should be okay. And then the good practice is you check. Okay, always check what you get is right or not. Okay, if you compute A inverse, try multiply A and A inverse together, see you get identity or not. This is always a good check. Okay, I think not many people have issue on this. Okay, question 2. Question 2, find the basis of null space, column space, and row space. Okay, so in principle, you might row reduce two different things. Okay, but actually what you are reducing is actually just A. Okay, so row reduce your A, and then check that how many pivot column you have. Okay, let's check, for example, this is the RREF form. Okay, so actually I also show you how I mark this question. So I straight away go and look for the RREF first. Okay, if REF turn out to be wrong, then I need to check whether your raw reduction step is correct or not. So let's go to the REF and then straight away pick up the pivot column. Okay, so you can see that there are two of them here. We use, okay, two. Okay, so let's say first I want to solve for null space. Okay, null space. So null space is on the right hand side, you replace as zero matrix, a zero vector. So the free variable here is how many free variable? There are two free variables, which are x3 and x4. Okay. So two-dimensional, then you need to produce two-dimensional basis for me. So how to get it? You need to get the parametric form. Okay. So here some people have issue how to find the parametric form of this solution here. Okay. So first you should realize that, okay, first I need to say this. So first you should realize that this matrix here, okay, is equivalent to x1 plus 0 times x2 plus 3 times x3 plus 0 times x4 equal to 0. Okay, and then second line will transform into 0 times x1 plus 1 times x2 plus 2 times x3 plus 1 times x4 equals 0. Okay, and then the last row is 0. So in the end, what do you get? You really get x1 plus x3 times s3. Maybe a bit small, is it? Okay, let me something away. This one already know. Okay. So let me write. And then this one is 0. And then the next one you get is x2 plus 2x3 plus x4 equals 0. Okay? And then from here, what do? You express s1 in terms of s3, and then s2 in terms of the rest, s2 and s3. Okay, only from here, you transform into the x solution. So x solution is what? x1, x2, x3, x4. Okay, So x1 we already compute is minus 3x3. S2 is what? Minus 2x3 minus x4. S3 is what? S3 is 3. So S3. S4 is what? S4 is 3. S4. Okay. So from here, go to here. Okay. Some of you still have issue of doing this. Okay. So from here, how to go to here? So you need to group all the S3 together, group all the S4 together. Make sense? Okay. So you group all the S3 together, group all the S4 together. So you will split this matrix, this vector into those with X3, those with S3, and then those with S4. Okay. So this is a step-by-step split. If you already know this step-by-step, you can straight away go to what you want. But this is the complete step for how you find it. Okay. So from here, you can factorize your S3 out. And then factorize your S4. Okay. Yeah. So this is a step-by-step how you go all the way from here to here. If you already know this step, actually you can straight away go from here to here. Straight away go from REF, you can see this vector out, right? Okay. So you can see that here is like here. Okay, so this is the basis of A. So as I said last time, so basis is a set. So you really need to put a set notation. Okay. If you say basis consists of vectors, okay, no need to put. If a basis is, then you need to put a set notation. Basis is a set, a set of vector. Okay. Uh, yeah. Okay. And then, yeah, some of you when you find the null space, right, you give me these two vector instead. Yeah, you give me these two vector. Okay, so this is just columns, some column space. Okay, this is not a null space. Null space live in the row. Okay, so you can see that null space here is in R4. Okay, this live in R4. Column space live in R3. Okay, column space live in R3. Okay. Okay, so how to find the column of A? So I already remind you in the class that don't pick the pivot column, okay? Because the column space will change after row reducing. Okay? So because for example, right, if you pick 100 and 010, okay, you can never make up number in the third entry here. Okay, these two zero term here cannot make up the third entry here. You see the third entry here all non-zero. You get what I mean? You get what I mean? Mm. You get what I mean? So you cannot use the row reduced column to find your basis. Okay, because the column space will change after row reducing. Okay, in this case, what is the pivot? Pivot is the first and the second column, which is 100 and 010. But linear combination of these two will never create these four vectors here. Can you see it? Because the third entry is always zero. Okay, so you cannot create non-zero entries in the third entries. Okay, make sense? Okay, so some of you still did the mistake, but this is different for row space. Okay, for row space, you can pick the one that is That's from the raw reduced one. Okay. Or you can pick the original row correspond to the pivot column. Okay. So for row space, for basis of row space, you can choose either from the reduce or non-reduce that correspond to the pivot row. Okay. To the row that contain the pivot. Yeah. This one I think most of you doing okay. For base. Some of you pick the reduced one, some of you pick the non-reduced one. I think some of you pick mix of them. Yeah, a mix of them. As long as you don't pick two linearly dependent one, then it should be okay. If they are linearly independent, then there's some issue there. Okay. Okay, cool. This one done. How about next one? Next one. We move them together first. Okay. Okay, next. Find the coordinate vector of x with respect to this basis. Okay, so this means you want to find a linear combination of the basis elements. Okay. Express x in terms of the linear combination of the basis element, and then the coordinate vector of x is just the coefficient. Right. So to solve this is what? Vector equation. Solve the vector equation is to solve the augmented matrix. Okay. Solve the augmented matrix, so you can solve. Okay, solve until you get this identity. So this identity tells you what? X1 equals to -2. Okay, in this case we use C. C2 equals to 0. C3 equals to 5. 1 times C1, 1 times C2, 1 times C3 if you prefer. So the coordinate vector of x is -2, 0, and 5. Okay, so good practice, check it. Okay, so check it, plug -2 into here, 0 into here, 5 into here, and then see when you add up, you get x or not. Okay. So I think most of you got it right for this question. Yeah. Most of you get it right. Okay, and then the last one. So the last one, could a 5 times 7 matrix have a two-dimensional null space? Okay. I know that a lot of you have issue understanding two-dimensional subspace and R2. Hopefully, after my explanation just now at the start of lecture, you have some different idea now, right? Because two-dimensional subspace refer to what? Subspace with basis that have two vectors. Okay, so the basis is two vectors. But R2 is what? R2 is a vector space that, okay, the dimension is 2, but it has a specific description. The elements look like x1, x2. Okay, but subspace here depend on this one. This depend on the nature of the subspace. Okay. So depend on where the subspace live, the element inside is different. Okay. But R2 already fixed is x1, x2. They are the same in a way that they have the same dimension, but they are usually different. Okay. Of course, we say that these two are isomorphic, but they are not different. Remember, we say in the start of the class, they are isomorphic, but they are not equal. Okay. Okay. So can 5 times 7 matrix have a 2-dimensional null space? So 5 times 7 is what? 1, 2, 3, 4, 5 on the row, and then 1, 2, 3, 4, 5, 6, 7 here. Okay. So at most you can get 5 pivot. That means you must have at least 2 free variables. Okay. So the answer here is yes. Okay. This question, how can you answer? You just need to give one example is enough. Because it asks whether can or not. Can or not. If can, give an example. Cannot, then you need to prove it. Why cannot? Okay. So you give an example. So let's say if every column form a pivot column has pivot, then the matrix span R5, very good. Okay, because every row have a pivot, and then the column live in R5. Okay. Take the matrix as A. Since, okay, this one very important because you don't want to repeat the matrix again. Okay, so you name the matrix as A. Okay, next time you say since rank A equals to dimension of now A equals to n. Okay, now in this case is 7. Okay, so 7 minus 2 is 5. So we can take rank A equal to 5. Okay, this means we take every column is every row is the pivot row. Then we can get that the dimension is 2. Okay, any question? Any question? Okay, let's see who get 20s. So we have Zhao Zixuan. Where is Zhao Zixuan? Okay, get 20. Gao Lu le? Gao Lu not here with me. Okay, Hu Zimeng. Hu Zimeng. Okay, Hu Zimeng. Zhu Qian. Zhu Qian also get 20. Liang Jingchao. Who is Liang Jingchao? Get 20. Sun Kailu. Okay, Sun Kailu always ask me stuff in team. Zhang Zitang. Okay, just now. Zhang Zitang. Zheng Fanghao. Okay, Zheng Fanghao. Good. Zheng Fanghao quite consistent. Both. Zhou Rui. Zhou Rui also got 20. San Qing. San Qing finally got 20 last time. Wan Ye. Yeah, Wan Ye also quite consistent. Zhang Zhou. Zhang Zhou also got consistent. Ao Jing mentioned already. Talia not here. Where's Talia? Hey, Talia at the back. Okay. Jiang Xingyi at the front. An Qixuan, let me know. Let me see who are you. An Qixuan. An Qixuan. Okay. MBT is what? Huh? Oh, Marine. Okay, okay. Zhao Xilei. Zhao Xilei. Just now we met. Duan Tianci. Duan Tianci here or not? Not here. Oh, at the back. Okay. Finally, you are here. Zheng Peng. Yeah, Zheng Peng. Good. Jiang Xiaoyi. Jiang Xiaoyi. Jiang Xiaoyi. Not here. Lin Ranzhen. Yeah, Ranzhen. Lin Yuqian. Okay, good. Liu Yunhao. Liu Yunhao, I think that's Liu Yunhao. Not here. Liu Yunhao. Yunhao. Ah, okay. Luo Yingjie. Okay. Xu Nianhe. Yang Qingya. Yang Qingya, just now saw you, right? Okay. Nianhe not here today. Okay. Good. Zhao Jing. Zhao Jing got. Keller in front. And then tester. Thanks. Good. Yeah, anything you want to ask tomorrow before lecture, we can discuss again. Anything from today? we can deal with it again. And any more question regarding quiz or please return your quiz before you leave, okay? And we'll see you tomorrow at 8 o'clock.可以放开这个，这样就是 open up。Yeah。是，我看到有点怪怪的。是，没有错。
老师，那个
是的 ，attendance。
门道里面把你拿出来。
啊，我知道他跟我说了，他刚刚跟我说。对 ，N 加
这个必须是也。都是求那个 run space， 那必须是 R 也。不行，那我可以写 X 了，你上面 DX。
喂，你干嘛？
我求 run space。
啊，你求 run space 对。
可以写 X2等于这张 DX。
哦，那 space 一定要 RAS，然后你是说可不可以写 S2等于那个？
对，
不可以，因为你看下面有 S2等于一些东西啊，所以如果你那么改的话，意思说你把 S2变成 S1，那就可以啊
X。
呀。
反正最后随便取，
就是你意思说你用OK，
我不写 X
啊，你不写 S3你就变成 S1了啊，可以，
也可以啊，
也可以，但是你的 S3那一项就变成 S1了哦。
对，
你没有啊？这个就变成 S1哦。意思说，
那这样的话，刚刚那个
就有一个这样。对啊，
刚刚那个，就是刚刚那个。这个的话，如果是说，它不是算出这个 x 1 x 2来，
对，
然后就算出 p 了，然后我换一下的话 ，p 的位置会不会变？
会，那个 eigenvector 和那个 eigenvalue 的位置是相对的，
也会变。那最后答案是算错了还是算对了？
没有，你为什么会变？你那个等一下我想一下。不会，你只是在那个 basis 里面找不同的 vector 吧？
对，
不会变，
也不会变，
因为你是在那个 basis 里面找不同的 vector 吧？懂什么意思吗？
大概，反正就不会变，
不会变，不会变。我还以为你是说这个位置换的话，还是这个位置换？不会。你的那个，因为你看我这个整个乘2我也可以有，
对，
我这个整个乘3也可以有。
那上面这个的话
明天是会读，
是，
是跑到
第4行
chapter 4，
那个会有就是 upspace 题，它是有，就是它是比较抽象的那种理论，还是会有给具体。是它是理论的题，还是像是这种会给这种
给这种proof subspace 嘛，
就是一个 proof。
对。
OK，然后这个的话写错了。
哪一个写错？
它这个算出来 A 不是应该是下面的？
对。
它这里相当于写错了。
对，这写错了。
那后面会改正。
会改正。这个其实我也没有算出什么东西，其
实下面不是算了。
下面是算了，对，我一定会改。我如果那个改过了会是对的东西。对，我这个其实也没有算出什么东西，我只是说要这样算吧。其实我没算什么。
但是这个是对的。
哪个？
就是这个。
对，这只是方法吧，还没有算出来其实。
其实数字是错的，但是方法是对。
对。
好的。
对，我会改。
我们明天也是4个题。
捡到了也就听一下，那边。
但是你是算错对不对？ 然后你不知道你哪里出错，看不出啊。那个翰林呢？翰林的对还是错？没看的。
你不是最后答案是错的吗？
对呀、最后答案是错的，但是他
我没看出来变在哪里。
怎么这个忽然间多一个一出来？
这个
OK，
耶，
对，
有东西有地方没懂。
哪个？
那个在下面。
哎，啊，什么？
你老师说进去了吗？
啊，我说进去了干嘛？啊，等下哦，OK，好。